start. And this is the final session.
Recording in progress.
This is the final session of the seminar 9 for LPHYS'23, and we will have 4 talks in this session, and looking forward to really interesting discussions. So the first speaker will be Kazuhiro Yamamoto from Kyushu University, and he'll be talking about testing the quantum nature of gravity. Okay, please start.
Okay, thank you very much. Thank you very much for the introduction, and I thank you very much for the organizers for giving me the chance to talk at this conference. And today I'm going to talk about quantum nature of gravity. And this is my talk is based on the collaboration with Dr. Matsumura and Daisuke Miki, Tomoya Shichijo, and Yuki Sugiyama from Kyushu University, and Dr. Matsumoto from Gakushun University, and Naoki Yamamoto from Keio University. And I will in my talk, in the first part, I will first give a brief introduction to quantum nature of gravity, and then I will give a brief review of theoretical basis of optomechanics. And then I will describe our recent work on generating entanglement in optomechanics due to electromagnetic force, and a theoretical model of optomechanics with suspended mirror. And then I will discuss Newtonian gravity-induced entanglement. And then finally, I conclude my talk. Okay, let me start with introduction. The boundary of classical mechanics and quantum mechanics is an important subject of fundamental science. And quantum mechanics is the law of microscopic world, and but gravity and general relativity is the fundamental law of macroscopic world, and the most massive object realized as a quantum system is 10 to 9 gram cantilever. On the other hand, the smallest mass whose gravity is measured is 90 milligram. There is no measurement of gravity constant smaller than 90 milligram object. So, measurement of gravity has not reached the mass in quantum regime. So this means that it has not been verified whether the gravity follows the framework of quantum mechanics or not. And to answer this is a simple question, and we consider, does the gravity follow the framework of quantum mechanics? And when gravity follows the quantum mechanics, superposition state of gravity or space-time curvature is predicted. And for example, if you assume particle A in a spatially localized superposition state like this left state and right state, and you prepare another particle B near particle A, then particle B will be in a superposition state due to the superposition of gravity force from A. Then this is a simple prediction, but this has not been verified whether a superposition state of massive object generates superposition state of gravitational potential or not. And this superposition of gravitational field is not trivial. Schrödinger-Newton equation to include gravity to quantum system is known. And in this approach, mass density of particle is given by square law of wave function, and potential is given by solution of Poisson equation, and the Schrödinger equation is solved with this potential. So Schrödinger-Newton equation follows a theory in which only matter fields are quantized but gravitational field remains classical. So gravitational potential is not an operator in this approach, and superposition state of gravity does not appear. To answer the question, does the gravity follow the framework of quantum mechanics? Recently, experimental proposal by Bose et al. And Marret Bedrar has attracted interest. And following their proposal, you assume two particles, A and B, each in spatially localized superposition state, left state and right state, like this. And then you consider time evolution through the gravitational interaction as operator. And this time evolution generates entangled state, like this. This is because phase of the unitary evolution due to gravity depends on the distance between position of each localized state. So if gravitational potential follows quantum mechanics, entanglement will be generated due to gravitational interaction. And they argued that generation of entanglement can be a test of quantum nature of gravity because the entanglement is generated only through the inseparable quantum interaction. And you may consider, instead of particles, you may consider two massive oscillators, gravitational interacting like this. And you may consider Newtonian gravity-induced entanglement generated between two oscillators in quantum state. And this is an example. This figure shows an example of time evolution of entanglement. It's a logarithmic negativity. And this was first discussed by Krishnanda et al. And they showed that quite low temperature near ground state is necessary, but the Newtonian gravity-induced entanglement is generated. And to detect the Newtonian gravity-induced entanglement, the key is the gravitational interaction between massive objects in quantum regime. And more massive objects are advantageous because larger signal of gravity is obtained. And the optomechanical system is promising to generate massive object in quantum regime. And the optomechanics consists of cavity light and mirror oscillator. And this mirror is one of the boundary of the cavity. And the cavity, a cavity light is standing waves, and wavelength changes when mirror oscillator moves, which describe the coupling between them. This is the coupling term. And we consider the optomechanics with continuous measurement and feedback cooling. And we include a laser. We can consider Hamiltonian, including the input laser power, and we can derive the equation of motion in this system. And you introduce amplitude quadrature x and phase quadrature y, and we consider the perturbations around steady state in this system. And we consider a dissipative optomechanical system, and we extend the equation to include the dissipation and the noise and the feedback cooling. This is the extended equation for oscillators. This is the dissipation term, and this is noise term, and this is the feedback cooling term. And these dissipation and noise included to satisfy the fluctuation dissipation relations. And similarly, we include the dissipation and the noise included for the cavity light equation of motion like this. And kappa is dissipation. This kappa is equal to decay rate of escaping of photons from cavity, and delta is called the tuning. And optomechanics and continuous measurement, and we consider optomechanics under continuous measurement and feedback cooling. And X is the measured output right. And this measured output right X is related to the input right in cavity by this equation. This equation is called input-output relation. And this determines how the output right observed in detector is related to the position of the mirror by continuous measurement. And actually, this is the relation between the observed output right and mirror's position. And these terms are noises. And the feedback cooling is a process to cool the mirror's motion using the information of continuous measurement of the position of mirror through the output right. And the feedback cooling increases the dissipation, and dissipation effectively increase the dissipation with preserving the noise correlation, and which reduces the temperature effectively. And we can estimate the variance of the oscillator mirrors like this. This may be a very complicated technique, but we further consider the Wiener filtering of the variance of the mirror. And when property of the noises is known, we can use the Wiener filtering process, and this minimizes the uncertainty by estimating the position from the measurement of the output right. And in the case, for example, for the position of the mirror, the Wiener filter is determined by this variance of the output right and the covariance between the output right and the position of the mirror. And using this Wiener filtering, we can obtain the minimized variance of uncertainty. And this is called conditional variance. And similarly, we have another components of the conditional covariance. And the state described by this conditional covariance is called conditional state. And using these techniques, optomechanics with continuous measurement, feedback cooling, and optimal quantum filter is a promising technique to generate quantum state of massive mirror. And the quantum control of optomechanical system is a technique in progress. And Dr. Matsumoto in Gakushin University is developing this technique. And in these works, they are developing quantum control of optomechanical system. And they demonstrated that sensitive measurement of sensitive displacement sensing of Brownian motion of an optically trapped 7 milligram suspended mirror. This is mirror very small, and with the sensitivity 10 to minus 16 meter per squared hertz. And they have already realized the lowest dissipation, this value. And they have also showed that, demonstrate that the mechanical squeezing state, it's a conditional state through the continuous measurement. They already demonstrated this conditional state. But for now, the purity is low. It's 10 to minus 4 order. But generation of quantum state near the ground state is expected to be realized in the near future. And next, let me describe our recent work. It's a feasibility study of generating entanglement due to the electromagnetic force. Detection of gravity-induced entanglement is quite challenging, so we should set a medium-term goal towards the final goal, and generating entanglement between milligram scale macroscopic mirrors due to half beam splitter is a good project. Using this project, we can develop techniques toward the final goal. And in our recent work, we studied the feasibility of generating entanglement between 2 milligram scale mirror in optomechanical system. And we show that it is possible to detect the entanglement between such massive mirrors experimentally generated due to electromagnetic force in the near future. And we use, in this analysis, we use Fabry-Perot-Michelson interferometer with power recycling mirror. And we assume a continuous measurement of common mode and differential mode of 2 mirrors, and feedback control and optimal filtering process, and which makes both the modes squeeze the state. And this power recycling mirror makes asymmetry between the common mode and the differential mode due to the difference of decay rate. And its asymmetry is essential to realize the quantum entanglement. And when common mode and differential mode are in each indifferent squeezed state with high purity, the mirror A and B are entangled. And conditional variance matrix of mirror, conditional variance matrix is second order moment of position and momentum of mirror A and B. And the conditional variance is given by the, in this case, given by the covariance matrix of the common mode and the differential mode, which are derived in the same way as the case of single mirror. And when the common mode and the differential mode are symmetric, entanglement may appear due to this component. And this figure shows the example of Wigner distribution of common mode and differential mode. And asymmetric distribution may appear due to the asymmetric decay rate. And this figure shows the logarithmic negativity, contour of logarithmic negativity on the plane of quantum cooperativity and detuning. And entanglement appears inside this dashed curve region. And this black black dot is the parameter, experimentally feasible parameter reported in the previous work. So entanglement between milligram scale macroscope mirrors can be realized in the near future. And this figure shows the common mode and the differential mode, Wigner ellipse. They are in different squeezed state is high purity, and this produces the entanglement between 2 mirrors. And I can skip this. And next, I explain theoretical model of optomechanics with suspended mirror. We are developing a more realistic model of optomechanics with suspended mirror, including the effect of dissipation and noise in mirror motions connected to dissipative beam, and also a finite size effect of mirror. This figure shows a schematic plot of the model, and it's a theoretical model based on the beam model coupled to cavity light. And this is the cavity, and this is the mirror oscillator. And this mirror is suspended by the beam, this. And due to the finite size effect of mirror, there appear two modes. It's their pendulum mode. It's a motion of center of mass pendulum mode, and another is a rigid. We call rocking mode or rotation mode. It's a rigid rotation, body rotation, and this mirror is connected by the elastic beam. We can extend this beam into inelastic beam, and this is described by a string-like variable and cavity light, and their degree of freedom we consider in this analysis. And this is a Hamiltonian of the beam model coupled to cavity light, and we can derive the equation of motion for these degree of freedom, and using suitable boundary conditions. And we repeat the similar analysis for this system for the perturbative equations, including again dissipative term and noise. And sorry, I skipped some details, but we found that the model is this model is effectively described by the two-mode theory of coupled oscillator, pendulum mode, and rocking mode in the low frequency region. And we studied the feasibility of generating a quantum state by evaluating the conditional variance with evaluating the Wiener filtering, applying the Wiener filtering process based on the two-mode theory. And this is the phase space distribution of the state, Wigner ellipse, and we used the experimentally feasible parameters reported in the previous work, and conditional state, conditional squeezed state with high purity can be expected when we use a two-mode Wiener filter properly, and entanglement between milligram scale macroscopic mirrors in Fabry-Perot Michelson interferometer can be realized in the near future. And next, I discuss Newtonian gravity-induced entanglement. The feasibility of detecting Newtonian gravity-induced entanglement, the pioneer work was done by Professor Miao and his group, and they consider two oscillators gravitationally interacting, and they investigate the signal of gravity-induced entanglement in output light, and they obtained this condition, this very low temperature. They concluded so very low temperature is necessary, and the detection of gravity-induced entanglement is quite challenging. And this is because weakness of gravity. This is a Hamiltonian of gravitationally interacting harmonic oscillator. And in this gravitational interacting harmonic oscillator, a common mode and differential mode are decoupled. And the effect of the gravitational interaction appears only for the differential mode. And its effect is described by this parameter. Rho is mass density, and omega is frequency. And this parameter is very small in general. So signal of gravity is very weak. That's the reason why detecting the gravity-induced entanglement is quite challenging. And we are doing reanalyzing the condition for detecting the gravity-induced entanglement. And we found that found the condition.
Sorry,
Yes.
time is up. Can you finish pretty soon? Sorry about that.
Yes, yes. Okay.
Sorry.
This is the second final slide, and yeah, condition is very challenging, and it's beyond what we can achieve in the near future. This is consistent with the result with the previous work. And this is a conclusion. Quantum nature of gravity is the subject which has not been verified at all. And Newtonian gravity-induced entanglement is useful for the verification, and it is necessary to generate massive object in quantum regime. And the optomechanical system is promising to generate the quantum state of massive object, where the feedback cooling with continuous measurement and the optimal filtering process are important. And it is also, it is possible to detect the entanglement between milligram scale mirrors, which makes up Fabry pair microsome interferometer. So entanglement generated through electromagnetic interaction is possible in the near future. But the detection of gravity-induced entanglement is quite challenging. But the feasibility should be studied further, including the other possible signal of quantum nature of gravity other than the entanglement. This is the final comment. Thank you very much. That's all I want to say. Thank you very much.
Thank you very much for a very interesting talk. Any questions? Any questions?
Hey, I have a question.
Go ahead.
Thanks a lot for the very, very interesting and clear talk. I wanted to ask on your opinion on realizing similar measurements in other systems, such as levitated nanoparticles, for example, which are much more lighter but have some other maybe advantages.
Sorry, comment? Sorry, question? Sorry, I could not get your comment.
So I was asking, can you comment on the feasibility of some other systems, such as levitated nanoparticles, in similar type of measurements as here proposed with the mirrors?
I know levitated system could be a possible way to generate and detect gravity-induced entanglement. But I think in general, levitated system could be that this dissipation could be large. So maybe going to deep space could be a useful approach to reduce the noise and dissipation.
Right. Okay. Thanks for the comment.
Okay, so maybe. Oh,
May
sorry.
I have one?
Okay, Homa-san, you're the organizer. Go ahead.
But yeah, I just, because you showed many parameters, so that I'm totally confused. But anyway, could you summarize how far you are standing now to your goal by taking one parameter, for instance? Because in the third paragraph, you said it's a promising way, but I don't I don't know how it's promising. I mean, how far we are now to your goal.
Okay. I'm not an experimentalist, so our work is collaboration with experimentalist Matsumoto-san, and we are using parameter in feasible in the previous study. So this generating the quantum entanglement using electromagnetic interaction is very feasible. I think that it can be generated in the 3 or 5 years.
Oh, that's very short time scale.
Yes, yes. But generating gravity-induced entanglement is very challenging. So we
okay. I see. Now, how much challenging? I mean, what is a fundamental problem? Just you have to develop new theory or new setup, or just matter of
maybe,
rejection of noises, and which is
for detecting the gravity-induced entanglement, it is very challenging now. So I think that we should consider the possibility of detecting another way of another signal of quantum nature of gravity. For example, squeezing. Squeezing is easier to detect entanglement. And as I showed,
sorry, we're kind of getting pretty far over, so maybe
sorry.
can you two kind of discuss offline?
Yeah.
Is that okay?
Yeah.
Sorry. So sorry. Let's thank the speaker again.
Thank you very much.
Sorry about that. Okay, so let's go on to the next speaker, and it's Young Kun, if I'm saying it right, Liu. And you have 25 minutes to give your talk. So.
Okay, so yeah, is it clear?
Yep.
Okay, thank you very much for the introduction, and thanks to the organizer for the invitation. I'm Yongkun Liu from National Taiwan University. So today I want to briefly introduce our project called Analog Black Hole Experiment via Laser, in short, ANABL. So here's the outline of my presentation today. First, I want to briefly talk about how we propose to use high-power laser to study the information loss paradox issue in the black hole physics. Second, I want to update our R&D status of several key elements. So let me quickly start from the black holes. So black holes, as we know, were predicted by Einstein's general relativity. And in the recent years, like the Event Horizon Telescope or the LIGO-Virgo collaboration detect the gravitational wave from two black hole merging events. So this shows that black holes are not just theoretical objects, but really existing in our universe. So in the early study of the black holes, Bekenstein and Stephen Hawking, they try to formulate a formula to describe the entropy of the black hole. Then how to understand black hole has entropy? So we may start from the thermodynamics, then we can use a temperature to describe a macro state. But if we zoom in into the object, then actually there are lots of possible macro states. So this is how the concept of the entropy comes in. Similar things happen in the black hole thermodynamics. Then to describe the black hole, we only need three physical quantities: the mass, angular momentum, and the charge. However, as we know, the black holes may be formed from different objects, from like planet, from interstellar gas, or anything. So what is microstates? Actually, this issue is still an open question, that how to count the microstates of a black hole. Is black hole entropy is equal to Boltzmann entropy or equal to thermodynamics entropy? This is still an open question. And if we look into the formula for the black hole entropy, actually, it's quite interesting that it combines the thermodynamics, general relativity, and quantum mechanics all in one formula. And it's quite strange that the black hole entropy is proportional to the surface area, capital A here, rather than the volume, like the normal object. So after the study of the black hole thermodynamics, Stephen Hawking realized that actually black hole is not that black, but emitting the Hawking radiation. And the so-called Hawking radiation is a thermal spectrum. Then the temperature of the thermal spectrum is inversely proportional to the mass of the black hole. So we may imagine that how the Hawking radiation happen is that if we consider the vacuum fluctuation happen around the event horizon of a black hole, Then in the normal case, then the creation, the particle and antiparticle will just create and annihilate. Nothing happened. But if in some case, one of the particle or antiparticle drop into the event horizon, then the partner mole cannot no longer catch the particle drop into the black hole. So from the outside, we will feel that the black hole emit a particle or emit an antiparticle. So this is a illustration of the Hawking radiation. And actually, Hawking radiation leads to the so-called information loss paradox I try to explain in the following cartoon. That as we just shown that the black hole may be formed from different objects, and different objects carry its own information. However, when the black hole emits the Hawking radiation, since Hawking radiation is purely thermal, so there's no information carried by the Hawking radiation. And but the Hawking radiation will take away the energy or the mass of the black hole. So the black hole will shrink. The black hole size will shrink. So in the end state, the Hawking radiation takes all the energy and mass of the black hole, then the black hole evaporates. But if we consider in the initial state that there are lots of information drop into the black hole, during the evaporation, there's no information going out. But in the end, there's no information left. Then the question is, where is the information? So if we write down this rigorously write down the process into mathematical form, then we can realize that actually this information loss paradox is means that the probability doesn't conserve, which violates the fundamental assumption of quantum mechanics. So this information loss paradox was first pointed out by Stephen Hawking in 1976, and after that, endless debates. So there are lots of proposed solutions, include this is still not a full list, lots of proposed solutions. And the reason, the naive question is why we don't directly measure the Hawking radiation in the universe. The reason is that the evaporation rate is too slow, or the temperature of the Hawking radiation is too low for astrophysical black holes. For example, the typical mass of an astrophysical black hole is around 10th of solar mass. Then the corresponding temperature of Hawking radiation is just 10 to the minus 9 Kelvin, which is very small, very low temperature. And the temperature is even lower for larger black holes. So considering this, then the analog black hole ideas are promising. Actually, it's interesting that the idea of analog black holes is almost as old as the Hawking radiation. So it was first proposed by Bill Unruh in 1981. He proposed to use fluid to simulate the space-time around the black hole. So this idea is called sonic black hole. And after that, several ideas were proposed. And for example, in the Stan Howard's group, tried to use Bose-Einstein condensate to mimic a sonic black hole. And they already did some evident result on the thermal property of the black hole radiation. And in the 2017s, Professor Pison Chen and Jerome Muhu proposed an idea called analog black hole evaporation via lasers. So the physics behind this project is based on the so-called moving mirror model. So what is a moving mirror model? So actually this theoretical work describes the interaction between a scalar field, let me call it phi here, interact with a time-dependent boundary condition. For example, if we force the scalar field vanish on the boundary condition, means that phi equal to 0 on the boundary condition, then this condition corresponds to a perfect mirror case. If the mirror is moving with some non-trivial trajectory, then the mirror will give non-trivial particle spectrum creation. This phenomenon is also known as a dynamical Casimir effect. So for example, if the mirror is moving inertially, then there's no particles generated. But if the mirror follows certain trajectory, for example, the famous Collis-Wiley trajectory, then the spectrum of particle is a thermal spectrum. This corresponds to an internal black hole means that the temperature of the black hole is constant. And different trajectory give us different particle spectrums, therefore corresponding to different black hole evolutions. So in our proposal, then we hope to realize the moving mirror through the relativistic flying plasma mirror. And we hope to control the trajectory through tailoring the plasma density background. So before talking about the flying plasma mirror, let me quickly recap the idea of the plasma wake field acceleration. So this was first proposed by Tajima and Dawson using the laser as a driver. And several years later, Chen et al. Proposed to use charged particle as a driver. When the driver propagates traverse inside the plasma, it will excite the wake field. When the driver is not as strong, then it's just a linear wake. It's like the duck swimming inside the lake. Then the amplitude of the wake is small. But if the driver is intense enough, then the amplitude of the wake field will be huge, and it's more like a tsunami. Here is a figure shows that when an intense driver travels inside the plasma, then it can expel the electrons and form an ion cavity or ion bubble. Then the dense electron shell can form and following the driver pulse. So to use the dense electron shell as a mirror, this idea was proposed by Sergei Bratnov, and then later in Japan, KPSI, Masaki Kando-san, and Alex-san also did experiments to verify this idea. So about this topic, I think there are several excellent talks in the Tuesday's seminar. So here comes the conceptual design of our Annabelle project. Then we hope to realize the flying plasma mirror within a gaseous target. The gaseous target is from a supersonic gas jet, and we hope to introduce a knife blade to introduce the shock wave, then control the density profile. When the intense laser pulse propagate inside this plasma target with gradient, then the flying plasma mirror will follow a certain trajectory. And this, from theoretical estimation, then we expect there will be Hawking photons and also its partner photons emit. But the Hawking photons are quite weak. The signal are quite weak. They are single photon event. So we need some single photon detector to detect these Hawking photons and the partner photons. So last year, we published the concept and the R&D status of our project in the journal Photonics. And here is the whole collaboration, includes La COSPA and NTU in Taiwan, and Ecole Polytechnique, CA, France, and QST KPSI in Japan. So currently, we are in the R&D of key elements phase. Then we are doing the R&D of several key elements. I will update some of the information about this part later. And from this year, we joined the experiments in KPSI. We hope to, this is for diagnosing the plasma mirror dynamics. And about the full-scale experiments, our goal is we hope we can detect the Hawking radiation and also the entanglement between the Hawking photons and the partner modes. Yeah, but since there are lots of the R&D is still quite challenging, so we hope the full-scale experiment can come in soon. So there's still no schedule for this. Okay, so next I will go to the R&D of our several key elements. So about the relativistic flying plasma mirror, so we did 2D peak simulation with epoch code, and to study we hope to find the optimized parameters for generating the flying plasma mirror. And we hope to study the curvature and also the amplitude of the density of the electrons in the flying plasma mirror. Besides, we also perform 1D peak simulation to study the reflectivity of the flying plasma mirror. Here, just one of the figures shows that the incident wave reflected by the flying plasma mirror has been compressed and the double Doppler boost to high frequency. And next, we also study the relation between the plasma mirror dynamics with a tailored background plasma density. For example, if we design the plasma density in this specific form, then we found that in the late time, the trajectory of the mirror will follow the so-called Debye-Fouillé trajectory in this form. And the special point of this trajectory is it can be used to mimic analog Hawking radiation with a temperature inversely proportional to the capital D. Here, capital D is a characteristic length of our density profile. With the design parameters in this paper, then we expect the energy of the Hawking photon is around 0.03 electron volt. So the right-hand side is a figure from this paper that we did some simulation. We did a comparison between the theoretical estimation on the mirror velocity to the peak simulation. So basically, they agree well with each other. But it should be noted that in this case, the plasma density is around 10 to the 17th, which may not be an optimized density for the flying plasma mirror generation. So we are still searching for the optimized parameters for the flying plasma mirror. So next, this is a theoretical work. Our colleague tried to extend previous study on the moving mirror model. Previous study just discussing the 1+1D perfect mirror. However, the flying plasma mirror actually is a semi-transparent, and the size is finite, and it's a finite size and finite thickness. So our colleague tried to derive the particle spectrum considering this effect. And we can, based on this formula, we can also estimate the number of analog Hawking particles emission per laser crossing. Actually, it's a very small number. It's just 10 to the -3. So we can also play with the number to assuming the repetition rate, 1 laser shot per minute, and typical 8-hour running time per day, and 20-day experiment. So we expect, with an ideal detector efficiency, we expect we will get 43 Hawking photons. I should admit that this number is still optimistic number, since we need to do some assumption on the parameters for the flying plasma mirror. Then we choose some optimistic parameters to get this number. So maybe this can be treated as an upper bound for our proposal. Next, I want to talk about the gaseous target, R&D. Since spectrum of the analog Hawking radiation highly depends on the dynamic of the mirror, so we need to well control and characterize the dynamic of the flying plasma mirror. So currently there are 3 working items. First, we hope to have the diagnosis of the flying plasma mirror. And then in our lab, we need to set up an image system for the gas jet density profile characterization with very high resolution. Our goal is to reach around 1 micron resolution. Third is that we need to prepare the gaseous target with a required density profile. Actually, it's a quite unique density profile. It's a 1+ exponential decay. It's a very special kind of density profile to realize the specific mirror trajectory. So in the last year, we joined the BISO experiment in KPSI, the PI of the project, Alexander Piroshkov, was one of the collaborators. So we take this chance to set up the probe line with Sherwood and shuttlecraft modes for the diagnosis of the wake field. In the right-hand side, I just try to take one of our data that we have main post here. Then this is ionization from of hydrogen, sorry. And then it looks like we obtain some possible image for the wake field. But we are still confirming this, the detailed data analysis is still ongoing. We hope that we can publish this soon in the near future. Next is about our supersonic gas jet characterization. So we set up a quantitative rainbow Sherwood image system in NTU. Current resolution for our image system is just around 10 micron. So the left figure is a Sherwood image of a supersonic jet into 1 atmosphere ambient. The reason to show the supersonic jet into 1 atmosphere is because under this condition, there are abundant features of the shock wave of the supersonic jet. For example, there are lots of oblique shocks, Mach disk, expansion wave, and so on. So basically from our image, then we can capture most of the features. So we believe that our image system is not enough, it's promising to continue to capture even finer structure around the shock wave. In the right-hand side, we show the sharing image of the of an oblique shock induced by introducing a knife blade. So detailed data analysis is still ongoing about this. So next, I want to talk about the possible backgrounds in our proposal. Since our signal is quite weak, then it's just a single photon event, and the wavelength is peaked at around 10 micron. So there are lots of possible background sources within this interesting wavelengths. For example, EMPs, terahertz signal, or thermal noise, or radiation from plasma waves or high electrons. Here is our plan to address these issues. About EMPs, we hope to estimate or measure it during the beam time using the NCU 100 terawatt laser or in KPSI with 1 petawatt laser. About terahertz signal, actually, is still unfamiliar to us, so I will not talk about this. About the thermal noise, since unfortunately the thermal spectrum emitted by object by the chamber with room temperature is almost the same around the 10 micron. So we need to somehow carefully design the cryogenic system to cool down all the chamber, or at least cool down the detector or the surrounding environment to prevent the thermal noise. About the last part, now we are investigating this issue with peak simulations. So this work was done by Naoki Watamura, and we run several 2D peak simulations, and we obtained the electrons trajectory, and then we developed the categorization algorithm to categorize the electron trajectory into different species. For example, snowplow, Wakefield accelerated, or some oscillating electrons. Then from this trajectory, we can calculate the corresponding radiation spectrum, then obtain the background spectrum. More details are shown in our photonics paper. So if you are interested in this issue, you can take a look at our paper. So last part about R&D is a single photon detector. There are several key requirements for our Hawking photons. First, since our Hawking photon is quite treasure, so we need the detection efficiency as high as possible. We hope to reach around 100%. Then since our signal is a thermal spectrum, so we need a broadband sensitivity in IR, and also low timing jitter and fast recovery. And besides, we also want to measure the entanglement between the Hawking photon and its partner mode. So we require the distinguishability of the polarization. With literature studying, then we realized that the so-called S9.12, the superconducting nanowire single photon detector, has the potential to meet all these requirements. So state-of-art S9.12 show 100% sensitivity at this near infrared, and with a short timing jitter and low dark count rate and polarization sensitivity. So our proposal is try to extend the current technology to the mid-infrared. The right-hand side is a photo of our first working S9.12 detector. The prototype now is working in the visible to near infrared. So this is a Raman figure of our nanowire structure. Okay, so in summary, that information loss paradox actually is a very fundamental issue in the physics. It may shed some light on the combination between general relativity and quantum mechanics. However, so far, most of the investigation are theoretical, or must. Yeah, so we hope that we can provide some way to direct observe the black hole end state. And we propose that the accelerating plasma mirror may serve to address some aspects of this issue. Then in short, then maybe our key requirements make our proposal is quite challenging actually. So, but we think that our R&D progress is still in good progress now. Yes, thank you for your attention.
Oh, thank you for a very nice talk. Are there any questions? Okay, Professor Keitel? Oh no, I'm sorry, you're clapping. Any questions?
Yeah, may I ask one question?
Oh, go ahead, please.
Yeah, on the so you try to measure the photon in the backward of the mirror.
Yes.
Why you don't try to measure the forward, which will have a higher frequency, which is much easier for detection?
Yes, actually, our goal is we hope to measure both, and the reason then we call the backward as Hawking photon is because the flying mirror move forward, and this backward photon actually experience the redshift. So this part corresponds to the redshift, like in black hole, the Hawking radiation also experience the redshift. So this part corresponds to the Hawking radiation. So our major goal is to measure this one. Yeah. So of course you are right, and to measure particle mode, the frequency is higher, so it's much easier. But yeah, it's not directly the Hawking radiation, analog Hawking radiation. Yeah, but we still need to measure the entanglement between. We hope to measure the entanglement between these two photons.
All right. Then the 0.03 eV is in which frame you are talking about?
In lab frame.
Lab frame?
Lab frame, yes.
It's an average temperature.
Yes, it's
because it should be forward region. You should have higher frequency, isn't it?
Sorry, can you say again?
For the forward direction, it's boosted so that I think in the lab frame you can define the lab frame temperature.
Yeah, true. So currently, from our theoretical estimation, then the backward it will be 0.03 eV, and the forward part we expect to be EUV photons. This depends on the gamma factor of the mirror. Yeah.
And I think the degree of correlation should be the same in between forward and the backward, and also some different portion of the forward emission. So, for instance, correlation between the light blue and blue. And I think you can get the equivalent information on the correlation. In such a case, it's much easier to try to measure the correlation in the forward region. And the first step. Yes. Do you agree?
Yes.
Yeah, because in terms of correlation, in any direction, you can measure the correlation. Then now, as a first step, we should try to measure the easier frequency domain. And then afterward, you try to measure with very specialized detector in the backward region, for instance.
Yes.
It's a kind of proposal or comment, okay.
Yes, think about comments, yeah.
Okay, so we gotta start the next talk. So let's thank the speaker again. Sorry to cut it short. And so the next speaker is Hidetoshi Taya. And Taya-san, can you get your slide up? And okay, and you have 20 minutes.
Okay,
thank you.
So, okay, thank you very
Go
much.
ahead.
Okay, thank you very much for the introduction and also this opportunity to give a talk. So I am Hidetoshi Taya from Weekend, and today I'd like to discuss the electric permittivity of the vacuum in the presence of a constant electric field. So let me begin with the idea of, Okay. So let me begin with the idea of how the change of the electric permittivity occurs in the presence of a strong electric field. Maybe you're already familiar with this topic, but let me just explain for completeness. So the idea is the following. So suppose we have a electric field or photon and want to inject it to some system. And if the system is just a vacuum without any external forces or fields, then this photon just propagates without any modifications. So this basically means that the electric flux of the probe equals to the value of the electric field strength of the probe. So that's all, nothing happens. However, the situation is really different if you have strong fields. So for this case, the strong fields coupled to the vacuum fluctuation, and so the vacuum is polarized. Then the injected probe will interact with the vacuum polarization, and in turn, its propagation is modified. So this means that the electric flux of the injected probe is becoming different from the value of the field strength, and this difference is quantified by this electropermittivity. So what I want to do in this talk is to calculate this electropermittivity. Now you may be thinking that this is actually an old topic, and there exists a number of studies. So you may be thinking that there's nothing new you can find by doing this study. But I would say that's not the case. And actually, I think I have 3 points here. So the first point is that, as I said right now, this is a very studied topic, but I would say the understanding of the electropermittivity is still incomplete yet. So the point is that in the previous studies, basically what they're focusing is the equilibrium situations in which they are only considering some magnetic field or constant cross field situations. So for which case, there's no energy supply from the external fields. So this is clearly different for the case of electric field. So for which case, the electric field supplies energy to the system, and therefore the system becomes essentially non-equilibrium. For instance, I think you maybe know about the Schrödinger effect, so which basically predicts that the vacuum decays in the presence of electric field, and so the vacuum evolves in time in some sense. So this is clearly non-equilibrium. So theoretically speaking, such an equilibrium situation requires some more careful treatment in theoretical calculations. For instance, the distinction between in and out states, and also the examination of vacuum particle diagrams and so forth. So the calculation becomes a little bit more difficult, and also conceptually becomes difficult compared to the equilibrium situations. But on the other hand, I must say that there already exist some studies for the case of electric field. So this is the famous result obtained in the 1960s. And what they are doing is essentially taking the derivative of Euler-Heisenberg effective action with respect to the probe electric field, and then they can calculate the electric flux, and in turn, they can obtain the real part of the electropermittivity. And this is what they obtain. But I think this formula is not satisfactory in various sense. So the first one is that obviously this formula accounts for only the second order correction by the strong field. So this formula cannot be applied to this formula is only applicable to the weak field stations and cannot be essentially extended to the strong field stations. So of course you can calculate the higher order corrections by calculating the higher order terms of the Euler-Heisenberg effective action. But in general, theoretically, it is known that such higher terms are known to be asymptotically divergent. So the validity of such calculation is not clear, I think. And another point is that this formula does not have any non-pathogenic factor like exponential or inverse of field strength. And because we know the existence of Schrödinger effect, which predicts that there are some non-pathogenic corrections in the presence of strong constant electric fields, so it's very natural to ask, is there any non-pathogenic factor in the Schrödinger regime for the case of electropermittivity? And the second point is that because the Euler-Heisenberg action is valid only in the slow field limit, and therefore this formula is basically valid only for the case of slow flow field, such that the typical frequency of the probe is much smaller than the typical gap size of the system. So the question that I want to understand in this talk is that what happens if I go beyond those limitations, namely what happens if I go to strong field or faster fields. And the second point is that I want to understand the vacuum structure of QED through the measurement of the electropermittivity. So the idea is the following. So suppose we have an electric field in this right direction, so which means that we have a potential, something like this. And because of this potential, we have a treated band structure, treated vacuum structure like this. So that is, we have a Dirac C and gap and the positive energy states, but those gap structure is basically treated because of this presence of electric field or this potential. So then interesting happened in the Dirac C. So that is, so now we have electric field in this right direction. So the electrons in the direct C wants to run into the right direction. And then eventually those guys hit this gap, and some of them will turn into the gap, so which is a source of the Schrödinger effect. And on the other hand, other particles are basically reflected by this gap. So this means that we have an incoming wave and also outgoing wave due to the reflection. So this means that there should be some interference between in wave and outgoing wave, and eventually leading to some oscillating structure in the distribution function of the electron in the direct C. So what is interesting here is that this sort of oscillating structure can leave some experimental signatures. So this is the case for the dynamically assisted Schrödinger mechanism. That is the particle production in the presence of a constant electric field plus some past electric field, past time-dependent electric field. So this plot shows the number of pairs are produced as a function of the frequency of the probe. So as you can see from this figure, you have some interesting oscillating behavior above the pair production threshold. And this is something you can show that originating from this tilted vacuum structure. So in such a way, for the case of a Schrödinger mechanism, you can discuss the tilted vacuum structure, but I don't know any argument about the case of electric permittivity. So through this study, I want to understand how this tilted vacuum structure is reflected in the electric permittivity. And what is interesting here is that such kind of oscillating structure of the electric permittivity are coming from the change of the ground state structure is already observed in the context of semiconductor physics. So this is the actual experiments made in 1960s, and what they are measuring is essentially the imaginary part and the real part of the change of the electric permittivity in the presence of and in the absence of electric field. So they are measuring those quantities as a function of the photon energy or frequency of the probe electric field. So clearly, we have some oscillating structure, and this is something you can show that originating from the change of the distribution function of the valence band electrons. So considering the similarity between the ground state structure of semiconductor and the vacuum structure of QED, it is, I think, very natural to expect something similar in the case of QED. So what I want to answer in this talk is that whether this is the case in QED or not. Okay, so now I think I have explained all the questions. So the first point is that the topic has already been studied a lot, but the understanding is immature, in particular in the strong and the fast field regime. And the second point is that I want to understand the reflection of the QED vacuum structure to the electric permittivity. And the third point is that I want to pursue the QED analog of semiconductor physics. Because I'm a theoretician, I did some theoretical calculations to answer those questions. So let me explain the theoretical part. So the theoretical part is really simple. Basically, what I have to calculate is the polarization vector by using the linear response theory. But let me explain this calculation one by one. So as setup, what I'm considering is the quantum electrodynamics in the presence of a constant strong electric field. And I inject a probe field, which is spatially homogeneous, but a period time dependent, so which is given by this Cardi E. And then I want to calculate the electric permittivity for this probe field. And for this, let me first clarify the definition of electric permittivity. So for this purpose, I first write down the total flux here, so which is, of course, sum of the total electric field plus some polarization vector. And in general, this polarization vector is a nonlinear function in terms of this E bar, strong field, and also this probe field. But now I am assuming that this probe field is weak, so I can safely expand this function P in terms of this weak field. Then you can obtain this kind of expression. And then massaging this, you can identify that the electric flux for the strong field is given by E bar plus the Z sort of term over the polarization vector. And you can identify that the electric flux for the probe field is given by something like this. And because the permittivity is defined as a linear coefficient that relates the electric flux in the probe field, so we can identify that the electric permittivity is given by this. So now my task is to calculate the polarization P1. So this can be done in the following way. So because we know from the electrodynamics that the time derivative of polarization gives you a polarization current. So that means what we have to calculate to P1 is to calculate this expectation value of the current operator in QFT language. But now what I'm interested in is the first order correction by the Pro field. So I expand this field operator in terms of the Pro field. Then you can obtain this sort of expressions. So what I have to do is basically to calculate this quantity. And basically that's all. And because in the presence of constant electric field, the Dirac equation is analytically solvable. So you can basically obtain an analytical expression for this upside zero, zeroth order term, and also first order term. And by using that, you can basically calculate this expectation value. And that's all. So now I'd like to show you some result. But before that, let me discuss some more theoretical details. So the first point is that the so-called Kramers-Points relation holds for the electric permittivity. So of course, this is something you can show generic. So of course, this is something you can show explicitly by using the explicit form of the expectation value. But you can also show this relation by the general argument based on causality. That means the response of the system can occur only after the injection of the Pro field. So by using that, you can generically show that the real part of the electric permittivity is related to the imaginary part of the permittivity through this Hilbert transformation. So in general, the calculation of imaginary part is much easier than the calculation of real part because the real part in general suffers from the UV divergence or normalization of quantum field theory, so which is a sort of subtle point of QFT. So it's in general difficult. But for the calculation of imaginary part, you don't have to suffer from such difficulties. So the strategy I took here is I calculate the imaginary part first, and then reproduce, then obtain this real part of the permittivity by using this Kramers permutation. I think it's worthwhile to be noted that the same kind of approach has been taken in the context of semiconductor physics. And because one of the purposes of this calculation is to pursue the QED analog of semiconductor physics, so it's very natural to take this approach. And the second point is that this may be obvious from the optical theorem, but I would say that I have to emphasize that this imaginary part of the permittivity is directly related to the Pell production number by the dynamically assisted Schrödinger mechanism. So this is also something you can show explicitly by using the explicit form of the expectation value that I have shown in the previous slide. But anyway, intuitive reason is the following. So the first point is that it is well known in the context of electrodynamics in matter. Imaginary part of the electric permittivity is related to the so-called dielectric energy loss. So which is the energy loss by the decay of the probe. And because the field energy of the probe field is given by something like this, and if you substitute the relationship between the electric flux and also probe field, you can basically obtain this expression. So the imaginary part gives you the dielectric energy loss. And on the other hand, from a microscope point of view, such sort of decay of probe should be caused by particle production. So we have particle production because the probe photon decays. And this particle production is related to the dynamic Schrödinger mechanism. And whenever a particle decay, whenever probe field decays, we have a pair. So we can relate the energy used for the production by this relation. So the energy used for the pair production is given by the number of pairs produced times the frequency of the probe field. So as I said, those quantity U1 and U2 should be equal to each other. So then we can relate the number of pairs produced by the dynamic Schrödinger effect to the imaginary part of the electric permittivity. So what we can say is that the dynamic Schrödinger mechanism is directly related to the imaginary part of the electric permittivity and indirectly related to the real part of the electric permittivity. So this also means that the measurement of real part of the electric permittivity is basically enough to observe the dynamic Schrödinger mechanism. In general, I think it's much more easier to observe the real part of the permittivity compared to the dynamic Schrödinger mechanism. So it would be nice for experiments. But anyway, those are theoretical details, and some of which I'm going to use at the later discussion. So please remember those details. Okay, so now I turn to discuss the results. So the first result is about the imaginary part of the change of the electric permittivity. So the left plot shows the case of the parallel field configuration, and the right plot shows the perpendicular field configuration. And this imaginary part of the permittivity are basically plotted as a function of the frequency of the probe field. So the most important message here is, as you can see from those figures, we have some oscillating structure, as I have expected from the oscillating Dirac structure. And what is interesting more is that this oscillating structure is clearly consistent with the semiconductor experiments as shown here. That is, we have a peak on the upwards, and after that we go down, and after that we have some oscillation. And precisely the same pattern you can see here. And the next point is that this imaginary part of the electric permittivity is non-vanishing, even at omega goes to zero limits. So here, so which is due to the non-perturbative effect, or can be understood in terms of the Schrödinger mechanism. So this is the argument. So as I said in the previous slide, the imaginary part of the electric permittivity is related to the number of pairs produced by the Schrödinger mechanism. And in the slow limit, you cannot use the Schrödinger formula to quantify the number of pairs produced. And if substitute that, you have this expression. And now I'm assuming that this flow field is weak, so you can always expand this expression in terms of this flow field. Then you can find that the imaginary part of the permittivity is non-vanishing by the factor of this non-perturbative factor. So as I'm going to show in the next slide, this gives you some interesting divergence in the real part of the permittivity. So let's see that. So this is the result for the real part of the electric permittivity. So basically the same things are plotted here. So this is the parallel field configuration, and this is the perpendicular field configuration, and those real parts are plotted against the frequency of the flow field. So the first important point here is that we again see some characteristic oscillating structure, which is coming from the change of the Dirac structure. And as was the case in the imaginary part, this oscillating structure is clearly consistent with the semiconductor experiments as shown here. That is, we have a small peak about here, and after that we have the biggest negative peak here, and after that we have some oscillation, and precisely the same pattern can be observed here. We have small peak, negative peak, and after that we have oscillation. And the second point is that we have some divergent behavior here, which is essentially which is the non-perturbative strong field effect. So this can be understood by using the Kramer's point relationship, because the real part of the electric permittivity is given by the Hilbert transform of the electric permittivity, imaginary part of the electric permittivity. And as I have said, the imaginary part of the electric permittivity is non-vanishing due to the non-perturbative effect at omega equals to 0. So then if you evaluate this integral, you understand that this real part of the permittivity should be non-vanishing and also logarithmically divergent by this non-perturbative factor. Okay, so this is the strong field effect, and also this is the fast field effect that I wanted to clarify in this talk. Okay, so I have explained everything, so let me summarize this talk. So the main results are shown here, and basically I have calculated the real and imaginary part of the permittivity, and see some interesting structure like oscillation and also the divergent behavior here. And those are the questions that I have posed in the beginning of this talk. So if I go to the first limit, we have some oscillating structure, which is originating from the change of the Dirac structure. And if I go to the strong field limit, due to the non-perturbative factor, or simply speaking, pair production by Schrödinger effect, we have some divergent behavior in the real part of the electric permittivity. Okay, so that's all of my talk. So thank you very much for attention.
Thank you very much. On time. Great. So let's thank the speaker. Any questions?
Yeah, I have.
Oh, that's surprising. Okay, here we go.
This energy axis is in units of electron mass. Is that correct?
Yeah, but it can be arbitrary because M can be arbitrary in principle, but yeah, you can think this as electron mass for the case of QED.
Arbitrary. So for instance, if in concrete, if we have 1 GeV gamma ray as a probe, okay, and with respect to laser field, and in such a case, how we can define this omega over M?
For that case, you have omega equals to 1J.
All right. That means it's too high.
Yeah, like I don't know, 100 or 1000.
Is that true? Well, I don't know. It should be center mass. I don't know.
So what do you mean?
I mean, okay. So if we use too high energy, then we lose this feature. So you
in principle, if you have really too high omega, then this, as you can see from this figure, this offsetting structure is decaying. So basically, you see something new.
Yeah, then your statement confuses me because you said the omega m it can be any scale, and then could you specify that should be the electron mass?
Okay, for instance, if you think about pion, then the 1 JeV scale, I mean, the omega equals to 1 JeV is not so large. I mean, pion mass is something like 400
right.
so it's something like here.
In this case, m should be the electron mass.
If you want to think about the pure QED, then you should take m to be the electron mass.
Okay, thank you.
Okay,
I mean,
so we have
what I'm thinking about is just a QED theory with arbitrary fermion mass. So you can choose arbitrary fermion. So in that sense, it's arbitrary.
All right, and I understand. Thank you.
Okay, Nakamiya-san, short question, please.
Okay. Okay. I have a question about the electric permittivity was coming from the Schwinger mechanism, which are relevant to the, for example, the direct production rate. This is connecting to the imaginary part of the permeability, and you can convert into the real part also. So how actually my question was the magnitude of the permittivity was determined by the actual rate of the direct electron production, or this is this is a question.
Yeah, yes, you can. I think essentially the direct production rate is equal to this number here. So by using this relationship, you can also the imaginary part of the permittivity, and then by using this Cramer's quotation, then you can obtain this real part of the permittivity. But the point here is that you have to measure the the rate of the production for the wide range of the frequency space. So that's
a wide range of frequency.
Yeah.
And also the kind of rate is important. Directron at time zero is quite many directron created at some time, because you are showing of the derivative of the U1 and U2. It's relevant to the number of pair production, I suppose. The time dependence of the pair production is important.
So can you say the question again?
You are showing the derivative of the U1 and the U2. It seems like the time slope of the rate of something. So we also need to, if we want to measure the permittivity, we have to measure the dielectron rate or the total number of dielectron from the Schwinger mechanism.
Sorry, I'm sorry. Maybe. Oh, sorry. We gotta go to the next talk.
Sorry. Okay.
So can you guys
it's not short. Sorry, I'm so sorry.
Yeah. So talk offline, and maybe it'll be clearer. Sorry. Okay. Thank you so much, Maya-san. Let's thank him again. And so we should move on to the next talk by Tomoyuki Maruyama. And he will be presenting on these vortex photons, correct? And you have 30 minutes.
Okay, thank you very much. Can you see my slide?
Yeah, it looks like you are showing
really? Sorry.
You need to switch to the other mode. Sorry.
Okay, the other mode. Okay, thank you. Sorry. One more again. Can you see it?
Okay, good. Thank you.
Thank you. Okay. My talk is titled is Photon Vortex Production in Synchronous Radiation of Electric in Relativist Quantum Approach. This is published in just a moment. Okay. Okay. This work was already published in Physical Letter B, and this is called my collaborators. And this has happened in astronomical systems. But recently, I also studied in actual experiment. Then Hajima-san joined our work, our group. Okay. First, I would like to introduce my work. Light vortex is also very familiar to people, all people so in this participant. Okay, angular momentums along beam directions. From this work, many people study that topics. And light vortex was considered to be artificial, not natural phenomena, is all people at first considered. But later, it was suggested that light vortex can be radiated from rotational black holes. It's a strong gravity systems. Then we can consider that it can possible to produce in nature. It may be natural phenomena. Then there is another strong field in astrophysics. It's a strong magnetic field in black hole and neutron stars. About 10 to 12 to 10 to 15 Gauss. It's very strong, so that it might be possible to produce light vortex or gamma ray vortex in these systems. This is my motivation in this start. And another motivation is optical radiation in synchrotron radiation, Kato-san et al. Okay. Then soft gamma repeater, I will show. The soft repeater is it's same as neutron star with strong magnetic field. Then it's like such a very big magnetic field. Then emitting X-ray and gamma rays observed. It's a particle, so that it must be photon. Then direction emitted photon go to perpendicular to the magnetic field case. It's a linear polarization, and if with photon emitted to the direction of magnetic field case, it's a circular polarization. It's well known, but I think near the direction, so near the magnetic field direction case, it might be photon vortex. It's my first idea in this works. This another process is optical vortex production in magnetic field. I just introduce. Kato-san group perform the calculation of synchronous radiation from its magnetic field and show that light vortex can be produced in these systems. Then later, he also performed the experiment and to get such vortex phenomena in this experiment. But okay, that's a good job, and this might be very good motivation of our work. But photon vortex has not been confirmed in these calculations. Then simple ideas. If it's utterly well known, electron make a motion of circular motion in the magnetic field. It's very fast. If it's radiate the electromagnetic wave case, it must be cylindrical waves. And if in quantum mechanics, of course, it's circular motion, circumference divided by Dobroi wavelength case, it must be integer. So that it's called discrete orbital argument and discrete level appears. It's called Landau levels. Then, if electron transit from this orbitals, this function must be produced one photon. It has a orbital angular momentum. It's similar like this. Okay. I repeat again. Electron fields at Landau levels. Electron stays at Landau levels, and this transit between one Landau level to another Landau level case. Of course, photon is emitted, and this photon must be against it of our orbital angular momentums. So then it's a cylindrical waves. But if electron move very fast to the parallel to the magnetic field directions, this must be a helical motion along these directions. this is eigenstate of orbital angular momentum, and of course it's usual momentum case. And its emitted photon must be Bessel waves. It's the eigenstate of orbital angular momentum and usual momentum to the z directions. So before the explanation of my work, preliminary on satellite, high linear polarization of gamma ray have already observed. So that in future, I expect the gamma ray vortex will be able to observe. It can be observed, I think. Then this is my work motivations. Okay, I will show my calculations. In strong magnetic field case, I define the direction of magnetic field directions. And the electron has helical motions and at random level states. This is an eigenstate of the component of total angular moment. I wrote it ZTAM and also the component of momentums. Then transition to random levels. Of course, one photon emitted and produce one photon. It must be eigenstate of ZTM and PZ. So this photon must be photon vortex. It's with Bessel waves. Before that, I will show my, I explain the electron wave function in relativist framework, but this is not one. But this is also, just a moment, which one? This is Dirac equations. And then this is energy of energies. This. This is random level equation, and L is the component of orbital angular momentum, and this is one more quantum numbers. It's a known number of XY planes. This is the solution of uniform magnetic field case. Oh, sorry, before I forget to explain that I chose the vector field of magnetic field is this shape. It's a symmetry gauge. Then wave function can be written in these waves. Lambda and this is a 4 component. Of course, is different orbital angular momentum mixed here. Then single particle energy is given here. Then, but please show this is random numbers n plus L is. When L is larger than 0, okay, this is okay. But L less than 0 is also possible to appear. But please note, for example, the node number for experiments, please check, please note, because this L minus 1, negative L is unphysical usually. But in these cases, X is completely arbitrary. Then n larger than okay, but n less than 0 or this is n less than 0. This is my mistake. And less than 0 and L, it's right. This is my N is larger one. Okay, that's okay. Sorry, L less than minus 1 is a very shift of central positions. Yeah, this another wave electron has a circular motion with another axis case. It's considered so that we should consider only n equals 0. It's a circular motion around origins. Then I consider photon emissions. This is, I said, eigenstate of the component of orbital angular momentums. Then it emitted case. And this wave function, this is a shape of photon wave functions. It must be automatically becomes Bessel waves. It's automatically. Then this is a transition between random levels. And Bessel waves written here. which shows, but it's a Z component also mixed. Then we have two kind of two common eigenstates, transverse magnetic and transverse electric shape. Of course, QZ larger than QT case, Bessel waves. As QZ is much smaller than QT, it's a cylindrical waves. Then, these two waves are connected with Lorentz transformations. And then this is the decay width and emission pt of probability of vortex photons. I would like to show result. This is a case 10 to 13 Gauss and 10 to 8 Teslas. And I chose it initial orbital moment as 10 matter H bar case. In this case is here. And I checked the final node number 0, 1, 2. As I said before, NF equals 0 is the same central axis. NF1 case another axis case. But considering with the smaller angular momentum case, same axis is dominant. Then Keiko1 is a fundamental waves, but Keiko2 is larger than 2 is harmonic waves. This is photon vortex. And the photon vortex produce not smaller numbers. This is a decay probability width of transition field again. And I checked 10 to 13 Gauss, and I chose 10 to 13 Gauss case. And this is, 10 to 12 Gauss also. And 10 to 13 Gauss is the same as previous figures. But go to L equal 100, it's almost continuous. Then similar here. Of course, NF equal 1 contribution is a little bit appears. But go to smaller magnetic field case. Of course, fundamental wave is dominant, but small, also smaller, but it appears. And go to 100 case, also similar behaviors, but the small number, small angular momentum is a little larger. Contribution is not small. And then TM transverse, I know the transverse magnetic mode is dominant. And also transition and the energy spectrum here. This is chosen here. And this is 10 mega electron volt and 15 mega electron volt results. Of course, K equal 1 is here. This is dominant and the largest. But higher go to higher energies, larger angular momentum contribution appears. This is a photon vortex. And also energy region completely different. So that's the component of total angular momentum increase, photon energy increase. Then if we can observe the photon energy completely, perhaps we can know these reactions here. But the fundamental case a little bit of the Z, 0 and 2 are mixed, but this is different. And this is another energy regions, 200 MeV and 1 GeV case. Of course, this is a similar result probability. But also all contribution becomes larger. So K equal 1 increase of angular the component angular momentums down is not small, and then total is someplace different, same as that, similar to that. So more spectrum is very goes slowly down. Yes. I show Manfield dependence case. These are previous ones, 15 MeV case, 10 to 13 Gauss. Energy is 15 MeV case. Then 10 to 4 Gauss, 10 to 14 Gauss case, and to 20 to 12 Gauss. It's a large magnetic field case and small magnetic field case I showed. And small magnetic fields is separate. This is each contribution is clearly separated. And this summation is a small case. And energy region is clear. It's my present result. And then I will explain the recent work, photon vortex production in laboratories. In laboratory case, of course, about 10 Tesla it's 10 to 5 Gauss, and Raman raises 10 micrometers. In this case, random level number is 7.6 multiplied by 10 to 5, very huge random number appears. It's, I think it's very difficult to these calculations, but I noticed the approximate method because this, of course, two-dimensional harmonic oscillator wave function can be written here. This is associated Lagrange functions. Then this is integration. We need to this matrix element. Problem is we consider only 0, 0. The node number with xy plane must be 0. In this case, equation very simple. And I can write only one associated Lagrange functions. Then these functions, we can use asymptotic forms because LIF, this difference is small, we chose it. But and of course, initial and final angular momentum is very large, but we consider only the very small angular momentum photons, so that we can use these asymptotic forms. Of course, we cannot use this asymptotic form in the wave functions, but after matrix symmetries, after integrations, we can use these asymptotic forms. Then we check these asymptotic forms. This is the initial angular momentum of 200, and also 2, 5, 10, 20, different photon angular momentum case. This is the difference between initial angular momentum and final angular momentum case. Of course, 10, it becomes almost same. 10, this becomes 10 case, a little small difference appears. Of course, 20 case, difference becomes larger. But usually, we need to consider, of course, 1 to k equal 1 and 5 case. This must be good approximations. Then we use 10 to 5 or 10 to 6 random numbers, so that, of course, there's very good things. I checked in my numerically, of course, this 1/40 case, almost good. This approximation is very good. This is a present result. This case is same, but I use only a symptotic form case and 1, 2, 3 case. And I choose initial is 150 MeV and 1 HJB. This is energy spectrum. This is fundamental waves and total k equal to. Of course, I forget. Photon has a spin angular momentum, so 2, 3, 4, 5 is right orbital angular momentums here. Of course, it goes down very quick, largely, but so that energy is spectrum is very clearly separated. And total is I show total, but it's not clearly appeared because it's agreed with this each contributions. And this is a 10 Tesla and 10 micrometer of Lyman radius case. And it changed to larger Lyman radius case, this result. Total is a little different because it's not go down. Of course, strength becomes increase, but photon energy becomes a little bit decreases. And not now, of course, dominant mode is not clearly each regions, but this can be the result. Because for this relation is a energy of photon energy and transverse momentum relations. I checked it. 10 micrometer case, 100 meter case, and initially 150 MeV case and 80 JeV case. Of course, energy increase, photon energy must be becomes larger, but Ramirez increase case, photon energy becomes smaller. This is only kinematical conditions. That's basic things. And also, I calculate 20 Teslas and 100 micrometer Raman radius case. It's a random level number becomes 1.5 multiplied 10 to 8, very large numbers case. And this, but in this case, strength becomes larger than before, and photo energy also becomes larger. Then dominant mode is clearly separated in each energy, not clearly separate, but Hayakawa-san said it's easy to observe in these conditions, he said. This is my result, yes. Then what I would like to show how to identify the photon vortex here. I examine the areal photon densities perpendicular to the beam direction case, fundamental case, and Keiko 3 case. This is sorry, I forget, 150 MeV megaelectron per case. Sorry. And this is Keiko 1 fundamental wave case, no pose, only small blue is a small strength case. Very central is the largest and goes down, density decreases. But Keiko 2 case, this is photovol case. The central positions density is smaller, then higher, then goes down. Keiko 3 case is also similar result, but the empty region becomes larger. Oh, sorry, I said energy is in these regions. Energy regions here. Then we choose is 1/2 of the middle of this energy regions. Previously. This is the result for this one, and it will be and this plot of the strength is transverse radius of transverse directions. This behaviors here. Okay, fundamental case is I show only these regions, then goes down and it oscillates normally. But Keiko 2 case also similar to Keiko 3 case. And energy different, but of course lasers value, but behavior is very similar. So it doesn't depend so strongly in energy. This space component, space distribution is almost does not depend strongly of the initial energies. Of course, strength is much different, but this density, radius radial dependence is not so large in these calculations. This is my present result. Then, summary. I would say summaries. Then electron in strong magnetic fields in eigenstate of random levels. I calculate eigenstate of Z component total angular momentum. Then I calculate transition between two random levels. Then I calculate one photon emissions. This photon becomes the Bessel waves automatically. And then harmonical photons, K larger than 2 case, are emitted to direction of magnetic field. Direction of magnetic field. So that means Arctic or Antarctic from neutron stars, Antarctic or Antarctic directions larger. But of course, magnetic fields are distributed more complicated, and any direction it appears. So I say, as mentioned before, linear polarization direction perpendicular to the magnetic field, and circular motion to the direction parallel to magnetic field case. It's well known. But also vortex wave appears in standard magnetic field case to near direction parallel to magnetic field. And then I said these phenomena can be confirmed in laboratory. And theoretical question for laboratory, and of course, incident electron orbital angular must be much larger than emitted photon case. But in this case, alternate form of the associated Laguerre function can be used. Then it's very good approximations. So that 150 MeV or 8 MeV case, of course, the 150 MeV is photon emitter 0.1 or 1 eV. It's not so difficult, but 8 GeV key, 10 eV electron volt, 100 electron volts. So it's possible observed. And also I checked Lama radius 10 micrometer case and 100 micrometer case. Sorry, 10 to 7. Sorry, 5 is wrong. 10 to 7. It's also possible. Then future work. One thing is we have to consider the identical method of vortex photons. I also already suggested that we should use compton scattering and coincidence experiment for electron and photon coincidentally observed. And I reported that it's also possible to show to identify the vortex photons. And we should consider photon vortex absorption reaction into nuclei, because in nuclear synthesis, electron ion absorption is very important. But if vortex photons case, due to the selection rules is changed, so that this absorption rate must be changed. And of course, fundamental way is dominant, but this is completely energy region different. So it might affect nuclear synthesis. We should consider that. And photon bursts, and also I would like to calculate study the photon bursts propagating in direct gases. Then, and theoretical analysis of photon vortex production also in gamma ray energy regions. And using it's also a possibility. I also already started these calculations. Thank you very much. Thank you.
Okay, let's thank the speaker. Are there any questions? We have a few minutes for questions, if there are any questions for the speaker.
I have one question to confirm the concept of the single photon. Okay, as a particle physicist, we learned that single photon must be a spin 1.
Yes.
And then you mentioned it could be a higher spin state. Is that correct?
In lattice mechanics case, photon case, spin angular momentum and orbital cannot be distinguished.
Right, but anyway, if we could try to observe the gamma ray,
yes,
the single particle, then that gamma ray should have may have spin state different from 1. Is that really true?
Yeah, it's really, and I also calculated include this effect. And then, of course, but it mixed with different angular momentums, yeah? Because we can consider only the eigenstate of total angular momentums.
Right, but if we forget about how it's created, single photon is just a single photon.
Yeah, that's
and
okay.
It may have different from spin 1.
That's
Is it really consistent with gauge invariance?
Yes, gauge invariance. Yeah, so yes, but of course the spin vortex photon case. Okay, spin angular momentum value is also depend on the gauge. That's moment.
Right.
So that of course this is a wave function here. Because of course spin 1s, but this vortex photon considering this expand its plane wave case, photon is not moved to the directions, only another direction. So that mixed the component.
Right. Although I don't understand, but I need to
transverse momentum exists. So transverse mass exists in Bessel waves. So that
in such a case, the photon mass is 0 still. Is
So
that
yes,
true?
mass zero. That's it.
Mass
Yes,
zero.
mass zero photons, of course.
Okay, so sorry, we got to finish. So really sorry, Maruyama-san. So
Yes.
let's thank him. Let's thank the speaker and all the speakers of this session for a very interesting session. And if the organizers have maybe comments, this is the last session of this seminar. Do you have any kind of short comments to make, or should I just say we're done?
Well, as one of organizers, I would like to thank for all speakers to stay until the last moment. Indeed, this last session was kind of challenging session to mixing many various topics here. But at least I myself was very satisfied with this session. Yeah, but I hope next time we can meet in person in this conference, because I felt I want to continue to discuss with speakers. So next time we will see you in person, I hope. Yeah, thank you for coming and staying here with us.
Yeah, maybe thank you also from my side. Also, as one of the organizers, I think I completely see the same way as Kensuke. So I think I especially hope that the political situation gets better, that we can meet in person, and also that we're not losing, a large fraction of people who are not allowed to participate. That was, of course, a problem for us to organize it. You've seen there basically no Americans we have in the sessions, and there the rules have been stricter. But I think I'm satisfied as Kensuke is. I was quite thrilled by the talks. I mean, also this twist from that Kensuke brought in. I thought, this is this also the Japanese community. I think is really strong, and I mean, I like this direction, and it's really giving it more life. So I don't want to make it too long. So thank you also from my side, and also those especially who stayed till the very end. So that's tough. And, so it's late for you probably, I guess, already. So take care. Thanks for joining. Bye-bye.
Thank you.
Okay, see you, everybody. See you next time, maybe in person.
Yeah, hopefully. Yeah. Bye-bye.
Okay, see you. Bye.
See you next Monday.
Thank you. Bye. Thank you.